great, thank you so much. It is time now.
Yes.
All right, so we introduced the Schrödinger field and talked about Photon, Photon fermion.
Is it normal like a 0 to I think it's normal.
Yeah, it means like.
And quantizing the field to get boson and fermion is actually now pretty easy. You have done this many times, so you are getting warmed up with that idea. We also talked about the particle wave duality, that boson particle can end up becoming a classical field wave for the BEC, polarization condensate. In the case of fermion, we talked about pairwise condensate. So that the pair, couple pair, behaves like a classical wave. So in either case, we have seen this the duality that when you do the quantum mechanics, you start with a particle, you quantize it and get a wave out. And QFT, you start with a wave, you quantize it and get the particles out. But in either case, after you quantize it, if you go to coherent state, your wave function starts describing what looks like a classical particle, but not as a classical limit, but what a quantum description of how a classical particle should behave. In the same way, in the case of QFT, you start with a wave, you quantize it, you get particles out. But again, building a coherent state would allow you to talk about how particles collectively start to behave like a classical wave, and that's what we discussed both in the case of BEC and the superconductor. So that's what we have done by now. And the discussion we start today is really what Berkeley logo says. It's very light. We start discussions with the photons. So what we do is to apply the same idea we have done for QFT up there. In the case of photons, of course, we know what a classical wave we are talking about. That's an electromagnetic wave. And what we would like to see is the first step of quantizing electromagnetic wave and get the photons out. So that's exactly the same idea as what we have done with the Schrödinger field. So that's the discussion. And so the way we get started with, of course, is starting with the Maxwell equations. And we have 4 of them. So this is the Gauss's law. This is just that there aren't any magnetic monopoles to the extent we know. And some people have looked for magnetic monopoles experimentally. And there was one claim by Canberra and Stanford to have discovered magnetic monopole, but has never seen since. So one possible interpretation is that he has observed only one magnetic monopole in the whole universe, and nobody has seen it since then, which is a possibility. But anyway, so most of the time, we at least don't think such a thing exists, but it still might. There are people looking for it, and theoretically, that's an interesting subject too. But here, I'm assuming that such a magnetic monopoles don't exist. Then we have also 2 other equations you're familiar with, and so that's basically it. One thing you may not have noticed looking at this set of equations is that if you look at the number of unknowns, in these equations, 3 components of E, 3 components of B, so there are actually 6 of them, right? But if you count how many equations you have, here's one equation, here's another equation. This equation, both sides of the equation is a vector, so there are three components of this equation. And that's true here too. So both sides are vectors, so three components of this equation. If you add them up, you have 8 equations. That's unusual, right? You have 8 equations for 6 unknowns. Normally, you have such a set of equations where you have more equations than number of unknowns, you would not find any solutions. So actually, electromagnetism is somewhat special in that regard. Now, why do we then find solutions to this? That's because 2 of the equations up there, maybe I should have solved it. These 2 equations turn out to be trivial once you use scalar potential and vector potential. So as we have done already, when you write electric field and magnetic field using vector potentials, and looking at the second equation up there, divergence of B vanishing, because B is written as a curl of the vector potential, its divergence is trivially 0. And just in case you might have forgotten some basics about vector calculus, so this can be written as Bi being epsilon ijk, j derivative acting on ak, and summing over j and k. And if you take divergence of this, this is II and this Levi-Civita symbol is totally antisymmetric under interchange of any of these indices, in particular between I and j. But here, if you interchange I and j with the opposite sign, these 2 derivatives of course commute, so that ends up canceling against each other. So that's why this is trivially 0. So the minute you introduce the vector potential, then this equation is trivial. And the same is true with the third equation. Because you have this expression, now in terms of vector potential and scalar potential, if you take a curl of gradient also vanishes by the same reason that different derivatives commute against each other. So the only place that would remain is this, which means that this is type derivative of curl of A, and the curl of A is a type is magnetic field. So curl E is negative B dot. If you move B dot to the other side of the equation, that's the third equation among Maxwell's equations. So this is also trivial. So it turns out that when you use vector potential and scalar potential, number of variables is now reduced. One component of scalar potential, 3 components of vector potential, so altogether you have 4 unknowns. Now these guys are gone, then you have 1 plus 3 equations remaining. So there are 4 equations altogether. So now it makes sense. You have 4 equations for 4 unknowns. That's why we can find solutions to them. So even though the vector potential and scalar potential are introduced for the purpose of convenience, we always regard vector potential and scalar potential to be the degrees of freedom when you write down the Lagrangian or Hamiltonian. So the idea is to come up with a Lagrangian which reproduces reproduces these equations from the least action principle, and that Lagrangian turns out to be what I have written actually on Wednesday. And this is the part that gives you the electric and magnetic fields, and then you have the coupling. The charge density and the current density. And the idea is that you vary this Lagrangian with respect to scalar potential or vector potential, not with respect to electric field or magnetic field. So we regard this Lagrangian to be a function of phi, a, and it turns out that it also depends on a dot. So in analogy to mechanics, we always regard the Lagrangian to be a function of x and x dot. Then take x dot derivative to define p. The Hamiltonian is p x dot minus Lagrangian. So this is the process we have gone through already several times. So in the same way, what corresponds to x in our case is vector potential. But you still see something a little funny going on because scalar potential has no time derivative anyway. So that's yet another thing we have to think a little bit about what's going on in the case of electromagnetism. But anyway, so if you look at this Lagrangian, for example, phi appears only in E squared. So this thing now contains that. And then if you take variation with respect to phi, you have del phi, and the other piece is still electric field, and epsilon naught, plus, I took variation with respect to A naught is actually phi, sorry about that. I used the relativistic notation, which I'm going to use later on, but I jumped the gun. So this is actually the scalar potential. So taking variation with respect to scalar potential is rho. Del phi. And you use the integration by parts, so this actually turns into this equation, and here's epsilon naught. So that's how you can derive the first equation up there. And you do the same thing also for the variation with respect to A, and that will lead to this equation down there. You see the vector potential couples to the current density, that's on the right-hand side of the equation. This contains A in it with time derivative. So again, using integration by part, time derivative acts on E, so that's how you end up getting E dot. And inside B, you have curl A squared. You take the variation, integration by parts, let one curl acting on the remaining B. That's how you get this curl B. So that's how you reproduce the last equation of the Maxwell equation. So that's how we know that this is the correct Lagrangian to start with. Okay, any questions about this so far? Everything okay? All right. So then we just get started.
I have a question.
Go ahead.
So we're considering, because if we're in a medium where we have electric field and magnetic field together, so the two terms, because it is the A nu with the J nu. So I think we've talked about that in the last lecture, but I forgot how the last two terms come from, or like do I rederive it back to the Maxwell's equation, or do I go from Maxwell's equation to get the last two terms in the Lagrangian?
So right now, the argument I'm making is that assume we know Maxwell's equation, and we are trying to come up with a Lagrangian that reproduces Maxwell's equation. And because Maxwell's equation has the sources of the charge density and current density, we need to put that in so that we can reproduce the equations.
I see.
Okay? Anything else? Yes.
Can I just for can I restore the combination of the Lagrangian? Now we have the two parts, which is T and minus V.
T and minus V.
Sorry,
Sorry, say that again?
Lagrangian was defined to be T minus V, right?
T minus.
Kinetic.
Kinetic term minus
Kinetic
potential
term minus
is the
potential.
whole.
Yeah. Then what's the kinetic term in here?
If we want to use that language, then first two terms correspond to the kinetic term, E squared minus V squared,
Okay.
and the last two terms correspond to potential.
And the potential seems to be the two terms seems to and they could be written into A mu G mu, right?
That's right. Once you go to relativistic notation,
And
then everything can be written as the four vector tensors.
and why is A mu to be a potential?
Sorry?
What does it mean? Why is A mu J mu to be a potential? It is a potential.
So the definition of what the new notation is a T minus V. So T is a piece that has derivatives in time. And V is the piece that don't have derivatives. That's a distinction.
Okay.
And E and B have derivatives, these terms don't. So that's the separation between what we call kinetic terms versus what we call the potential terms.
Okay. Is there any actual physical correspondence to the A mu J mu as a? It's like, is there any potential that could be written into A mu J mu?
Is there any potential?
Yeah,
that
because
is-
we understand this no derivative part to be a potential, right?
Yeah, so if you, for example, look at phi and solve this, the Gauss's law, and in terms of phi, this turns into Poisson equation. And this is what we're going to actually do. So we eventually take the Coulomb gauge. I'm jumping ahead here. To simplify discussions, when you take Coulomb gauge, inside this E, there is A dot, but you take divergence of it, and in this case, divergence of A vanishes, so this A dot piece vanishes in the divergence E. So this ends up being only dependent on phi, but this can be solved right away, because then phi of x turns into dy 4 pi x minus 1 rho y, and is epsilon naught. This is just the Coulomb potential, right? And then you stick this back into this. Then what do you find? Is that that piece over there ends up being and now you can see this is the Coulomb potential among the charge densities. So that's how you can see that this piece ends up having the meaning of a potential.
Oh,
Does it make sense?
yeah.
Okay. So yeah, I jumped ahead a little bit, and I come back and mention this again. So, but anyway, so that's the idea. And let me forge ahead. So we talked about this expression of the electric and magnetic fields in terms of scalar vector potential to be redundant because there is the gauge ambiguity. And I need to make sure about the sign here. Even if you make these changes, the electric and magnetic fields don't change. So that's why this is the gauge transformation. And you can choose chi in a way you want to simplify your life. So you can always choose chi in such a way that it satisfies this Coulomb gauge condition without loss of generality. And the reason is that suppose you have vector potential that doesn't satisfy this, then you can try to find what chi should be so that the new A would satisfy this equation. And then what you're supposed to do is that I take divergence of the both sides. And we want the new A to satisfy the Coulomb gauge condition. So different side vanishes. This one didn't vanish. That's why I have to find chi to make them cancel against each other. And this divergence of gradient is nothing but a Laplacian. So all you have to do then is solve this Poisson equation. And we know the solution, which is the same form of the equation we had for the scalar potential. So we can solve this. This function at x is given by divergence A at y integrated over y. Then you can always find a solution to this, knowing what divergence A originally was. And using this chi to do the gauge transformation, the new A automatically satisfies the Coulomb gauge condition. So what that means is that you can always perform a gauge transformation that the Coulomb gauge condition is satisfied. That's why there's no loss of generality by imposing this Coulomb gauge condition. And that would enormously simplify the rest of the discussion, so we will stick to this. Okay? Any questions about this? You probably have seen this discussion in electromagnetism class. All right. Now that we have chosen Coulomb gauge condition, let's look at the Lagrangian again. And let's forget about this source terms right now. Just focus on the first two pieces. So Lagrangian density this, we stick in the definition. Then we already found the scalar potential can be obtained by looking at the Gauss's law for whatever charge density you have. So in the absence of charge density, that's the free photon I'd like to focus on right now, then this equation tells you that scalar potential vanishes. So if charge density vanishes, scalar potential vanishes. So I don't need to worry about scalar potential anymore. So now it's getting a lot simpler. Then I'd like to further simplify this term over here. So if I write this more carefully, what we are doing is this. This curl A squared is actually this because curl A is a vector. You dot that together with another vector over here. Then, as usual, we allow ourselves to do the integration by parts. So this would then be the same thing as negative sign. And this curl is now acting on the other one, which is the magnetic field over here. Then this is again a bit about the vector calculus. So this curl of curl ends up being minus gradient of the equations A plus Laplacian A. So if you work this out using this tensor notation, ijk, and this is the index I over here, and then I have k, ijk, del j, k, del m, l, k, m. It's summed over k, l, and m. And there's an identity that if you have product of two Levitsky symbols, k is common between them. So you either make I and L the same and J and M the same, or I and M the same and J and L the same, but then you need to interchange them so that comes a minus sign. So there's an identity that this is the same thing as I L J M minus I M J L. And if you look at this I L J M, then J is the same as M, so this derivative is acting on AM, and sum over J and M be the same, so that gives me this divergence A. And the other piece is delta IM, delta JL, delta J, derivative J, derivative L, J and L the same and sum them over, so that becomes the Laplacian. And the remaining index is A, J. So that's how you get the second term. So this is the way you can simplify it. But now that we decided to be in the Coulomb case, this term vanishes. So this starts getting a lot simpler because this piece here can be rewritten as A Laplacian A. And once you get to this flow, then we can immediately start thinking about complex. So as I said, Lagrangian is regarded as a function of the vector potential. And here's the time derivative of vector potential. So what I can do is to identify conjugate momentum, which I call pi. And taking the derivative with respect to A dot, that gives me epsilon naught A naught. And A is the canonical variable, pi is its conjugate momentum. So now we can write down canonical commutation relation right away. Namely, if you have I component of A, and position x, and this is the definition of the canonical momentum. And this has to be IH bar delta function. So this is the canonical commutation relation. Yes, Sarah.
Should there maybe be an extra commutator between I and J? Have to be the same?
Ah, thank you. I forgot to write it, delta ij. So only when I and j is the same, they do not commute, because for each component of AI, you find each component AI, if I use this index notation, I find pi I, which is AI dot. But if this index is different, that somebody else's canonical conjugate momentum, so they commute. So only when this piece here is the conjugate momentum for this particular A with index I, they have this delta function as the commutator, and hence there's a canonical delta ij. Thanks for asking, Sarah. Any other questions? Yes?
It's not obvious to me why rho being 0 implies that charge density.
So right now we're looking at case of electromagnetic field without sources.
So the Laplacian is 0, and why does it imply that the whole function is 0?
So you're saying that the phi could still be some function which satisfies this condition and non-zero? That's the question?
Yeah.
Yeah, so it turns out that when you actually want to solve this equation, the only solution turns out to be phi equals constant. So that's actually not very useful. So if you actually have phi as a constant, so you have A naught phi, phi as a constant, then if you actually look at this expression for the electric field, gradient of constant is 0. So even if you're trying to keep phi as far as you can go, it vanishes anyway. So that's why you can always drop it at the end of the day. Thanks for asking. Any other questions? Okay. And then, using this canonical commutation relation, we try to build the Hilbert space in a usual way. And one little reminder here is that this sort of is reminiscent of what we did with the original harmonic oscillator. X and P is M X naught, is 1, IH bar. XP is IH bar. So it's very similar to that. If this is X, this is X naught, and this is M. So what we have done with the harmonic oscillator would directly apply to in this case, which means you should be able to write X basically like A plus A dagger, P to be basically like A minus A dagger. So we can split AI and AI dot in a linear combination of creation and addition operator this way. So that's how we should be able to actually come up with the creation and addition operator. So I leave out the intermediate steps, but in the end, you can write AI of X to be some normalization factor, as you always get with harmonic oscillator, some of the momentum modes. I'm using box normalization here. So you can do this Fourier expansion and find this coefficient A and A dagger here. And AI dot is given by minus I and the point here is that there's a minus sign in I. So that's how you can see that what corresponds to X in a harmonic oscillator is A, written as A plus A dagger. But this is now a mode expansion in momentum space, so you need to have this plane wave factor. And to make sure that A is a vector potential which is a real field, which means permission once you quantize it. To make sure this is permission, if there's a plane wave with plus sign exponent, its conjugate should have minus sign exponent. So this is basically a unique combination we can use. And this normalization factor is fixed to make sure that it reproduces the IH bar as the correct normalization. And A dot is what corresponds to P, so it should look like A minus A dagger, together with I in front. And once again, AI dot should be a permission operator. I changes its sign under permission conjugation. So you have to make sure that this thing in the parentheses has a sign change under permission conjugation. And this permission conjugate is exactly this one, but because of the residual minus sign, they switch under permission conjugation, giving the minus sign overall that cancels the minus sign from I, and therefore AI dot is remission. So once you have this canonical commutation relation, remembering what you have done with the harmonic oscillator, you can immediately write this down. The only tricky thing you need to work out is this normalization factor in this box normalization we have been using all along. With periodic boundary condition. And once you do this, the Fourier expansion of the vector potential in its time derivative, you can work out what the commutation relation is among these creation relation operators, and you get the form which you would naively expect. So AI of P, a J dagger of Q, they have a commutation relation of 1 if P and Q refer to the same momentum mode, and if I and J refer to the same index. And once you see a form like this, I hope that makes sense, because now you see this, you can start building the Hilbert space. And one thing I forgot to mention is that this piece omega p is the frequency. The frequency is given by the wave vector, which is p over h bar times speed of light. Yes, Kay?
So I understand qualitatively that A I and A dot I in this form, but I also understand that the exponential of I p dot x over h bar is the understanding of propagation.
This ends up being really the momentum of the photon. So in the end, interpretation is very simple. AIP is the annihilation operator of a photon of momentum p polarized in I direction. And this one is the creation operator of the photon for the momentum q for the polarization in j direction.
So the p dot x is the propagation direction?
X is the argument of the field. Remember, we did field theory. So this is meant to be very similar to what we have done with the Schrödinger field. In the case of Schrödinger field, Lagrangian was this form. So this was already in the form that this was A dagger, A dot. So they ended up being conjugate to each other. That's how we had psi of x, psi dagger of y, the delta function. Then we just expanded psi of x in sum over the momentum modes AP IPX over h bar, psi dagger of x, P A dagger P, minus I dx over h bar, and some normalization factor here I don't remember, which depends on the size of the box. So in the case of Schrödinger field, the Lagrangian was already written in the form of annihilation and creation operator. So that's why we didn't need to have two terms in the Fourier expansion. But in the case of electromagnetic field, the Lagrangian looks more like the original harmonic oscillator Lagrangian of x dot squared minus x squared. That's why x, what corresponds to x is the vector potential, should have both A and A dagger in it.
Yeah.
What corresponds to P should have also A and A dagger in it with the opposite signs. So that's why we have to do the expansion in this way.
But I do have a question.
Yeah.
So now I have polarization direction and I have propagation direction.
Right.
I have polarization plane as well, and I don't know how to read off from the.
Yeah, that's the discussion next.
Okay.
That's when we have to remember that the Coulomb gauge condition should be imposed. So far, I just tried to quantize the field, and Coulomb gauge condition I didn't pay attention to. So now I have to start to pay attention to that, and then we find the meaning of the polarization vector coming in.
So, in other words, AI and A dot I doesn't depend on polarization.
No, it does, it does.
Only on the omega P?
Omega P is just the frequency of the photon. So P over H bar is the wave vector. C times wave vector is the angular frequency of the electromagnetic wave. And if you multiply H bar on both sides, this ends up being the energy of the photon.
Because I'm having a hard time to connect from Schrödinger field to the real scenario where I have polarization.
So we'll talk about polarization in a moment. So can you wait a little bit? Okay. Any other questions? Yes.
I want to ask if the P runs from minus infinity to plus infinity, or is it from zero?
In sum of P?
Yeah.
Sum of the P in the Box normalization with the periodic boundary condition is that you sum over all possible P's that satisfy this periodic boundary condition, which has to do with the 2 pi h r over L nx, ny, and z. And if this n and n are integers, then 2 pi h bar over L times integer times x is an exponent. H bar cancels. Then this is 2 pi integer times x over L. So if x moves by L, it comes back to the original phase and satisfies the periodic boundary condition. Same in y and z directions. So this sum over momentum is the same thing as summing over an x from negative infinity to positive infinity, and y negative infinity to positive infinity, and z negative infinity to positive infinity. That's the definition of summing over the momentum modes. So another hand, yes?
How do we know this is a bosonic field?
How do we know it's a bosonic field?
Assuming the
Yeah, we are assuming this is the boson. That's a good question. And if you look at this form of the Lagrangian, and if you assume that this is actually a Grassmann-Odd variable, then this is b squared. So you have bi. That's the half of bi anti-commutator. Then it vanishes. You multiply the same thing twice, and if it is Grassmann-Odd, that identically vanishes. So you have a Lagrangian that's identically zero, and that doesn't give you a useful theory. So the minute you see this Lagrangian, then you know already that you have to regard this as Grassmann even, and therefore that leads to a boson, and therefore that leads to commutation relation rather than anti-commutation relation. That's a very good question. Thank you for asking. Any other questions here? Okay. And before getting to polarization, so I have to keep a little bit more suspense for K. So Newtonian is given by P x dot minus L. So in our case, P is epsilon naught A dot. X is A dot minus half E squared p squared. And this thing is nothing but the same thing as this one except a factor of half. And this switches its sign. And then if you work this out using this A and A dagger, it turns out that's really given in terms of h bar omega p times A p I dagger A I p plus constant. And going from here to there is just to plug in that Fourier expansion into the definition of A and A dot and work things out. It's a little bit of algebra, but in the end result is very simple. This really looks like a harmonic oscillator Hamiltonian, that A is an annihilation operator, A dagger is a creation operator, and when you create one photon, then that gives you energy, excitation energy of h bar omega p. That's really the c times the momentum of the photon, and that's exactly what you know for the energy of the photon. So now you can pat yourself in the back, because one of the motivations why you started QFT was to understand where photons come from. You have the ground state now, which is annihilated by this annihilation operator AI of P. And when you act creation operator on this vacuum state, this is the state of one photon. When you add two of those, you have two photons, and so on and so forth. So idea of the Hilbert space is exactly the same thing as you have done with the Schrödinger field. So now, this is the moment you celebrate. You finally have seen photon in quantum theory. Okay, any questions about that? Yes, okay.
Yes, so.
Not polarization yet.
No. And we have the h bar omega p, right?
Yeah.
So in other words, does it mean that h bar omega p is not a proposed, okay. So photon in Einstein's interpretation is energy wave packet.
Right.
So it is not just the idea, it's just that it's.
We derived it.
Okay.
That's the question, right? So we
Yeah.
derived it.
Yeah.
There was no ambiguity in the whole process. We had well-defined Lagrangian that was meant to reproduce Maxwell's equation. So no ambiguity there. This was the unique Lagrangian that reproduces Maxwell's equation. Then starting from the Lagrangian, we just went through exactly the same process you have done with the harmonic oscillator. You identify X, you identify Y, a P, set up the canonical commutation relation. Then the only thing we had to do was this Fourier mode expansion, but otherwise it's exactly the same thing as harmonic oscillator. Instead of having just A plus A dagger, we had to add over all possible P's and index I. Also for momentum operator, A dot, we had this A and A dagger. Not just A minus A dagger, but we had to sum over momentum mode and index I. But otherwise, that's exactly the same thing as we have done with the harmonic oscillator. Again, no ambiguity, no wiggle room. And as an end result of it, you find photons of the momentum P whose energy is C times P. And C came from, if you remember, the only two constants we had is Lagrangian epsilon naught and mu naught. And the reason why C came out is that C squared is the product of epsilon naught and mu naught, inverse. So that's why C actually comes into this equation. So again, there's no ambiguity.
Then I have a quick question. So where did the omega p came from when we formulated that?
So this was supposed to be the correct normalization.
Yes.
So we would like to get this AA dagger commutation relation to be 1.
Yeah.
So I could have written all of these h bar omega p as Cp instead. h bar squared in this case. I could have written this way. And what you notice is that C is square root of epsilon naught mu naught inverse. So if I actually write it that way, then this is written in terms of epsilon naught and mu naught. This is also written in terms of epsilon and mu naught. So you don't need to introduce C, but at the end of the day, you find only this product is important. So that's why we are calling C at the end of the day. Okay? So as Kay noticed, the great thing about this is that we are just applying the standard technique we have developed over the last half of the semester, and there's no wiggle room. You just go ahead and do it, and find a collection of photons as the end result. So that's why we know the photon is a particle that corresponds to the quantized electromagnetic field. Okay? Yes?
Why do we have components for the photons?
Yeah, so that's the issue with the polarization. I'll come back to it in a few minutes.
Oh, sorry.
Sandro?
In the case of the harmonic oscillator, so at the beginning of the semester, it was clear that A and A dagger had a specific role, which was the one of increasing the state that we had. But in this case, we basically defined these new operators, which aren't necessarily the same thing, are they? I mean, how can we know that these two operators play exactly the same role by increasing the state, like the ground state, by 1 or like by 2 or by whatever?
Well, that's because first of all, we know the commutation relation.
Okay.
So if you focus on one P and one I, that's the same as the harmonic oscillator. We also have the Hamiltonian, which also looks the same as the harmonic oscillator.
Okay.
So we know the Hilbert space. The ground state is given by a state that's divided by A. Then you keep raising energies by acting A dagger on it. But the interpretation is that not just raising energy, you are literally creating a photon by using a dagger operator.
Okay, thank you so much. Yeah, makes
Okay.
perfect sense.
Any other questions? This is sort of a important point, Jackie.
Is there a reason why the P is outside the sum, like the omega P?
Uh-huh. That's because we put the system into the finite size box. If you want to use the infinite space, then the momentum space has to be quantized using delta function normalization, which is okay too.
Wouldn't P, even this vector here, like if
It
X,
should be inside the summation.
Sorry?
The
because
definition
P
of
can still vary in length?
So your notation question is about notation. Why I'm writing this omega sub P?
No.
No, sorry, why the omega
Two
P is
equations.
outside the sum?
The normalization factor, because now we have P.
Ah,
Yeah, yes, P
good point.
dependence.
Good point. I should keep this inside the sum because it depends on P. Yes, you're completely right. As a matter of fact, in my notes, I had this exponential square root factor inside the sum. For some reason, when I wrote this on the board, I switched the order. So you're completely right. Thank you. Any other questions? Yes.
So like for this given system, what we're doing is kind of like we are diagonalizing the Hamiltonian, and then can I say that for any given system, then I diagonalize the Hamiltonian, and then I will get something that looks like the eigenvalue times positive definite operator.
That's
and
right.
I just say that like we can recognize those excitation modes as particles.
Right. So as a matter of fact, we will be looking at other field theories later, and for spin zero particle, Lagrangian actually looks something like this. We'll take this one away. And once again, you have E's that goes like phi dot. We have A dot. You have the gradient phi, and B is basically the derivative acting on A. So the form looks similar, except that I have this additional term, and this ends up describing spin zero boson of mass M. And I think there's some factors of C and H on here. So it's the same idea. Once you have a Lagrangian, that is quadratic in fields. This is quadratic in A, this is quadratic in phi. And if you have a piece that has time derivative of that variable squared, in some spatial variable, some potential, you can always diagonalize the Hamiltonian using this technique and find a Hamiltonian that looks like harmonic oscillator. What ends up being this excitation energy for the case of spin zero boson is different because it has a mass. So this ends up being c squared d squared plus m squared c to the fourth for relativistic massive boson. But what you also see here is not just that the energy of the photon is linear to momentum, but it is also telling you the photon has no mass. And again, there's no ambiguity here. We just started from Maxwell's equation, build the Lagrangian, and then quantize it and found the Hamiltonian. The fact that energy goes like c times p, c was already given in terms of epsilon and u naught inside the Lagrangian, so that is derived. And we don't have m squared c to the fourth in this expression, which means photon is massless. And that is again the consequence, not an input. So everything has been derived. And for any Lagrangian of this type, with the two powers of derivatives, the two powers of field, can always quantize in a similar way, and we are going to do this later on, and find the Hamiltonian of the harmonic oscillator type, and that works no matter what. Am I answering your question right?
Yeah, my question is just like, so the term particle in quantum field theory can define that to be like the eigen excitation of the quadratic part of
Right.
the Lagrangian.
Right.
So that's right.
Right.
Okay.
And of course, in the end, we have to put in some interaction. And I'll show you one example in a moment. But the idea is, you always apply this idea, no matter what field you're looking at, you first identify the quadratic part of the Lagrangian, then go through this and find the Hilbert space and excitation energy. That is what we call the free part. Then talk about interactions later as a perturbation to the system. So that's the way we deal with the QFT most of the time.
Okay, thank you.
Yes?
You're saying that photon is massless because there's no mass in this
Right,
expression.
exactly.
Does that mean we can read off the masses of phonons and like bogons
Yes,
and other things
yes,
we've seen?
yes. And in some sense, the gap you have found for this, the fermion condensate, and you can call that as a mass, because by creating an excitation, it costs a finite amount of energy, minimum energy, and that corresponds to basically less energy in the case of the relativistic particle. What's your name?
Vibhu.
Sorry?
Vibhu.
Vibhu.
Vibhu. V-I-B-H.
V-I-V-I-H.
V-I-B-H.
V-I-B-H. Vibhu. Okay. Vibhu. Any other questions? Okay, so now I come back to a question by Kay about polarization. So right now, we have this AI P, and it's from the conjugate. But one thing we didn't impose is the fact that you have to satisfy the Coulomb gauge condition. So by acting Coulomb gauge condition on this Fourier expansion of the vector potential, and what you get for the A dot is the same thing, so let me actually erase this here. I just go ahead and write this out. The square root factor, which I don't bother to write. But when you take act derivative on this whole thing, x dependence is only in this plane wave factor in the exponent. So taking derivative with respect to x, pull out IP over h bar. So what I get is IP dot A into the IPX over H minus IP P dot A minus IT dot X H1.
Should be A dagger.
A dagger. So what you see is that this Coulomb gauge condition means Ti Ai of P has to vanish. And this is the origin of something, the fact you're familiar with. If you're talking about electromagnetic wave moving in z direction, then only direction you have electric field is perpendicular to it. You never have electric field along the direction of the electromagnetic field. It's always transverse to it. So this is the condition of the transversity. So what that means is that for a given P, for example, let's say P is along the z direction for now, I have Pi, Ai, but P is only along the z direction. So this is AZ that has to vanish. So we originally thought you had AX of P, AY of P, AZ of P, so three sets of annihilation operators, but now you know that there are actually only two. Once we impose this Coulomb gauge condition, this operator is identically zero. That's how we end up having only 2 degrees of freedom for the photon. And that corresponds to 2 linear polarization of the electromagnetic wave. Namely that when electromagnetic wave is moving in z direction, one possibility is that electric field would go like this along x direction. This is electric field. Then magnetic field is in y direction instead. Another possibility is that this is y direction, and electric field might look like this. In this case, magnetic field is in x direction. So you have 2 possible linear polarizations. But we don't have the situation where electric field points in the same direction where electromagnetic wave is moving. And that is actually a consequence of the fact that this operator just vanishes. Now, if you consider more general momentum, you can see it's a little bit more complicated. It's some linear combination of them vanishing. So that's when it is much more useful to introduce the idea for the polarization factor. So if P is pointing along some arbitrary direction, we introduce 2 polarization vectors. This is one of them. Another one. Is this. And if you look at this condition that P and the transverse polarization vectors, both of them satisfy this condition that P dot epsilon vanishes. That's probably easy to check. So for a given momentum, we introduce these polarization vectors. Then instead of using this expansion using AI, what we should have done is AIX expanded in P HR over 2 epsilon naught rho cube omega p, and then write epsilon 1 AP1 plus epsilon 2 AP2, both of them e to the I px over h bar, plus coefficient conjugate, let's say a dagger piece. So instead of treating three components of the vector potential completely independent from each other, we make sure that's expanded always in terms of these vectors that are guaranteed to satisfy the Coulomb gauge condition, and have associated annihilation operator for each of these polarization vector. So that's the way we now see two photons degree of freedom for any particular direction. And it's easy to see that this A, the same vector index over here, if you do divergence of it, then the divergence would pull out P vector out of the exponent. So you end up having P dot A epsilon, P dot epsilon. And by definition, they satisfy this condition. So the Coulomb gauge condition is automatically satisfied. And once you have done so, then you identify two degrees of freedom, which corresponds to these two polarizations of the electromagnetic field, now pointing in some arbitrary direction P. So that's now the end of the story. So the only little complication we had, which we didn't have in the case of harmonic oscillator, is that we have to impose this Coulomb gauge condition. So out of three independent components of vector potential, you end up having only two independent polarization vectors. And each polarization vector comes together with an annihilation operator. And so that the whole field now satisfies the Coulomb gauge condition. But otherwise, there was no ambiguity. Just starting from Maxwell's equation, you build the Lagrangian, you quantize it, introduce the canonical commutation relation, expand it in the Fourier series, and that's all you have done, except for this little issue with the Coulomb gauge condition. But that was it. Then you found the photons. Okay, it's a moment for a party. Now we have seen the photon. Yes?
What will happen if we switch another gauge condition like the Lorentz condition? Will we get the same result?
That's a really good question. And the answer to that question turns out to be rather technical. So instead of using Coulomb gauge condition, you can use Lorentz gauge. And because you can choose arbitrary gauge in your discussion, you are allowed to choose this gauge. So the little complication with the Lorentz gauge is that even if I impose this, you can have another set of Lorentz transformation. And using this Lorentz index, you can write it this way. And if you do this change, Lorentz gauge condition changes to this condition. And this piece here is pi double dot minus Laplacian pi vanishing. The problem is that this has solution now. In a case of Coulomb gauge condition, we could solve for the scalar potential, except for a constant term that didn't do anything. So namely, it was completely fixed. In the case of Lorentz gauge condition, there is still remaining degrees of freedom that you can do a gauge transformation to stay within Lorentz gauge, so that there is a still remaining redundancy. And that ends up causing a little problem. And if you would like to do so, it turns out, this is the technical thing, you cannot impose this as a condition on A mu as an operator. That will lead to inconsistency, it turns out. But you can impose this condition only when you take the expectation value of any states, and imposing this condition does not be consistent, but what is meant by this physical state is that your Hilbert space ends up having states which are not physical, which has negative norm. If you take absolute squared, you find -1 instead of +1. That sounds really crazy. But in order to accommodate this condition, you actually have to do this. So everything becomes more complicated. You can do it, but I wanted to avoid it for the purpose of this class. And so that's why I'm insisting on the Coulomb gauge condition for the purpose of this discussion here. So you can do it, but you have to live with this extra technical complication. And if you're willing to do so, go ahead, you can do that. But I wanted to avoid it.
Will the result be the same?
Yes, it turns out the result is the same. That had been proven.
So the consequence of Lorentz gauge condition is that we cannot determine our chi.
Chi still has a solution that looks like this. So if you have any function chi, which looks like itx minus omega t over x bar, where omega is c times b, then you can satisfy this condition. So you have an infinite degree of freedom left to stay within the Lorentz gauge, and that is the origin of this technical complication. Okay? So you can forget all about this discussion because we are not going to use it. Any other questions? Everything okay? And once you have this, of course, Hamiltonian also now has this polarization vector restriction. And then you have only sum over 2 polarization states. Namely that you have h of omega p, a lambda p, and you sum over lambda, and lambda is 1 or 2, which corresponds to each of these polarization vectors, but interpretations are again the same. So now we have the complete set of Hilbert space. This is the definition of the vacuum. This is a one photon state, and you can specify one photon with a pair of data, specify the momentum, and its polarization being either 1 or 2. If you have 2 photons, you use 2 creation operators. Then you have the state with photons. One photon specified this pair of P1 and lambda 1. And the second photon specified by P2 and lambda 2. So that's how you define your Hilbert space. Each time you create a photon, you specify its momentum and its polarization. And you also know that 2 A daggers commute. So I can freely interchange the order between them, which means this state is the same as 2 photons interchanged, which means that photons obey Bose-Einstein statistics as expected from the beginning of the discussion. Okay, any questions about that? Okay, I have 5 minutes left. So now that we have found particles, as we have always done, you don't have to go back to the waves too. Which means that I can talk about the coherent state of photons. By taking a particular momentum mode for now, and particular polarization, And you have looked at this state in the midterm problem as well. So usual thing, the only difference is the A dagger here is the A dagger of the photon, which creates a photon momentum P and polarization lambda. So I fix P and lambda for this discussion. Then this is the coherent state. Then what you can do is to compute expectation value of the vector potential in this coherent state. And if you take f to be real, for the simplicity of discussion, if f is real, f and f star are the same. So this ends up being 2f cosine e dot x over h bar. This ends up being I f sine e dot x over h bar. So now you see the vector potential is really behaving like a wave as an expectation value of the field operator. Then if you go ahead and think about electric field in a Coulomb gauge where we didn't have phi in it was nothing but the negative of this one. Magnetic field is the curl of this one. So you actually have, sorry, I forgot the polarization factor here. So that then I pull out P from the upstairs, so I end up having P cross epsilon over H bar. And here I have minus IP cross epsilon over H bar. Then, because of the minus sign, this ends up being sine. And in front you have P cross epsilon. Here you have epsilon. Then you find that electric field is in epsilon direction. So this is the direction where it's going. Then this is epsilon direction, that's the electric field. Magnetic field points to P cross epsilon. So that's perpendicular to both P and epsilon. So that's only that direction. And that's exactly what you know about the electromagnetic wave, namely that if this is the direction of propagation, electric field points one way, and magnetic field points the other way, and everything is orthogonal to each other, and that's exactly what you find. So again, this is the particle wave duality, namely that classical electromagnetic wave is a coherent state of photons. So if you take a laser pointer in your hand and release the laser beam, you are creating a coherent electromagnetic wave, and that is actually a coherent state. And if you are taking this Wi-Fi signal on your tablet, I guess any road, then you're receiving the radio signal, or probably 5 gigahertz or so. That's a coherent radio wave. That is actually a coherent state of photons. So the same idea as we have done with the BEC, once you have a field, you quantize it and find particles. But out of these particles, you can build a linear superposition of different number states to build a coherent state. And coherent state behaves as if it is a classical particle as you are doing with the midterm problem. So in the same way, if you have electromagnetic field, you quantize it and you find the photon. But if you build a coherent state out of these photons, you can describe what looks like a classical electromagnetic wave. But it's not really classical because it is meant to be an expectation value, an operator. So your description is still fully quantum, but you do find something that behaves as if it is a classical electromagnetic wave, and that's the particle wave duality as we have seen in many examples by now. Okay, and that's the end of the class today. Any questions? Yep, you should really celebrate now you finally see your photon in quantum theory. All right? No questions? Everybody happy? Very good.